This, my friends, attendees of Starship Congress 2017, may I introduce to you Alan Kay. Alan, where are you today?
Where am I? I'm in London.
London. In case you don't know, Alan Kay is one of the co-founders of the Xerox PARC Research Center. It's world famous. Founded in 1970 as a division of Xerox Corporation, PARC has been in large part responsible for such developments, things you may have heard of as laser printing, Ethernet, the modern personal computer, graphical user interface, and it goes on, object-oriented programming. Right, so Alan did an amazing talk. I don't know if it was his TED Talk or another one, maybe one for Google, and he said, he had this line, he said, if you want to be a millionaire, do something better than pick something and do it better than other people. But if you want to be a billionaire, do something that's never been done. Well, immediately that connected with me because I said, oh, that's like building a Starship. And so I contacted Alan, and by the grace of good, he's with us here today. Alan, I give you the floor.
So the next sentence after that is, if you want to make $1 trillion, start a new industry. This is where Silicon Valley falls short. They've forgotten that that's what happened in the 70s, and they're still working on the industry that was created then. Right now, they're loath to do the investments that would create a new industry. So they're basically stuck in just making millions and billions. If you advance things, you generally advance things by changing the entire context. And I'll say a couple of words about it. Let me see if I can share my screen here. Let me turn on this. Turn on down for a second. Can everybody see my screen? Okay, great. I'll turn it off again. So, when I think of Starships, in the context of this conference, I would think of this Vanguard, and some of you will recall its name. It's from a science fiction story by Robert Heinlein. It was published by the Jordan Foundation. It left on its voyage for Proxima Centauri a little over 100 years from now. So I thought it would be fun to show a memo from just 100 years from now about preparations for communications with air. I'm going to turn the sound back on because it helps, even though there's feedback, it helps to hear. Oh, it is? Okay, I'll turn it off then. Okay, so, and some of you will recognize the name Hoyland here also. And first thought for this talk would be to actually just write the rest of this memo and go through it, but then I realized it would be a couple hours worth, and I wasn't sure I could actually make a good 2 hours out of it. So I thought I would talk about some of the issues about communicating with aliens. And first, here's where this novella by Robert Heinlein was first published in Astounding in 1941. So I did not see that one. I was just 1 year old in 1941. But in 1950, 10 years later, for 10 cents, you could get this little slim paperback from Dell with the first of the 2 stories in it. And I got that when I was 11, and just for the hell of it, I looked to see what inflation has been since then, and it's still a bargain. It would cost 94 cents today. think most people in the room will have certainly read this story. For those who haven't, it's a kind of a Lord of the Flies before Lord of the Flies idea. There's a mutiny on board this generational starship. And the story is a few hundred years after this mutiny, and a almost Neolithic or maybe Bronze Age civilization in this starship has sprung up with religion and everything known to anthropology at the time, and nobody knows that they're actually on a ship. You just think it's what they're on. And this story really fascinated me. It just grew my mind, and it got me looking into anthropology and sociology, because it was a glimpse of human beings as completely malleable to new forms of culture, and particularly atavistic forms of culture. And if we look back on this timeline, and I hope there's enough resolution so you can see it, here we are in 2017, and it's interesting that in 1929, which is only 88 years ago, Hubble first found convincing evidence that our universe was larger than the Milky Way. He found that what we call nebula were actually galaxies, and from a variety of evidence it is deduced that they were immensely far away. So that was just 88 years ago, and Heinlein's story was written just 12 years after that, 1941. And of course they were going to Proxima Centauri, which is, I forget, some partners away. We now know that it has planets. England didn't know, but it was guessing that it did. And the Vanguard is supposed to go leave its moon's orbit and go on this voyage in 102 years. But it's worthwhile thinking about in the context of aliens that it wasn't that long ago that we couldn't detect any electromagnetic radiation except light. And the first commercial broadcast station in the U.S. was KDKA, which was in the early 20s. I think it was 1923 or 24. We didn't get interesting radio until World War II, with radar and so forth. Relativity we've had now, we just celebrated 2 years ago the 100th anniversary of general relativity. Einstein also did quantum mechanics, but real quantum mechanics really didn't happen until around 1925, so it's less than 100 years old. And computing, I'm over here in London, not too far from Cambridge, where arguably the first usefully programmable computer, EDSAC by Maurice Wilkes, was done in 1948. And so, as an idea, it goes back, of course, to Babbage and more recently to Turing, but computing as we know it today really started within my lifetime, comfortably within my lifetime, and much of it has happened within your lifetimes. And this whole span here, going all the way back to Galileo, is just about 400 years. And by mitochondrial DNA, we've been on the planet humans have been on the planet for about 200,000 years. And 400 years is about 1/5 of 1%. The 200,000 years we've been on the planet. Most of those 200,000 years we haven't done a lot. And so, even thinking about aliens and, let me just do a sound check. It's all coming through? Coming through? just the idea of contacting aliens and thinking it might be through electromagnetic radiation. If you look to the right, Hubble up there, you'll see the name Bell. Bell was one of the main guys who has elucidated quantum entanglement, perhaps a much better way of communicating over interstellar distances or galactic distances. Nobody knows whether there is a propagation velocity for entanglement. One way of looking at it, there has to be another way of looking at it. There doesn't have to be, but that's an interesting one. So the whole idea here is that most of the assumptions actually made by Robert Heinlein were done in his own time, like most of science fiction. Some of it has lasted, but I think we'll see that some of the assumptions that Heinlein made maybe should be remade. Now, an interesting side note is there was the equivalent of the Jordan Foundation in the 1960s, set up by this man. Art was set up as a result of Sputnik, and Lick, a few years after this, set up the funding agency, like the Jordan Foundation, to do what he called man-computer symbiosis. He articulated this dream. In 1962, computers are destined to become interactive intellectual amplifiers for everyone in the world, universally networked worldwide. And no matter what people asked him, he would just say this, and they'd say, well, how are we going to do it? He says, I don't know, but we're going to find the smartest people in the world and fund them. And so some of the principles of this old Jordan Foundation really advanced something very important. Visions instead of goals, and cosmic and romantic. Fund people rather than projects. Let the people figure out what's going on. Fund the best people. Fund problem finding, not just problem solving. One of the ills of our age, most people who are funding research want the researchers to tell them what they're going to do ahead of time, and the problem with that is basically engineering. So a nice sidelight that hooks into our conference today is this memo that Lick wrote in 1963, and he wrote it to the members and affiliates of the Intergalactic Computer Network. What is that, you might ask? Well, that's what I'm doing this talk over. And he said if we succeed in making an intergalactic network, then our main problem will be learning to communicate with aliens. And so this was the original name of what today we call the Internet. And the Internet is here today because this man funded the development over about 15 years to do a variety of packet switching, biologically organized networks until we started getting something like the Internet in the mid-70s. And what did he mean by learning to communicate with aliens? Well, he had some specific ideas. Three of them are these. First, if you scale something enough, for instance, if you scale a network to the entire Earth, you have people separated enough in culture and distance and in goals that might be hard for them to find common ground. And communication is about identifying things that people think they have in common. And language is a kind of a symbolic way of pointing at things that are in our thought cloud. So Lick was one of the three things. Lick was thinking people to people, and of course, multiple people with multiple people. How do organizations of people learn to communicate? And secondly, he was thinking about how can we communicate with computers. This was back in the 60s. There weren't any GUIs back then. And it was not clear what was on a computer's thought cloud. What you could see by peering inside of a computer was not anything that a human wanted to be able to or could think about. So computers were really alien. And certainly, if you're going to have a worldwide network, you're going to have zillions of computers and you're going to have a lot of people. This is a communication. And finally, you have this problem of what can computers say to each other if the computers are different? What kinds of common ground do they have? And I just added in a fourth one here, which is real aliens. Same basic idea. What's the common ground? How do you get the common ground? And so people to people, the language has the problem of not being terribly specific. When you try and describe something like an animal that has a mane and it has hooves and it eats grass and so forth, both people might think they're talking about a horse, but in fact, one of them could be talking about a zebra. And it's actually a joke in the medical community. I will explain that joke if somebody's interested after the talk. So this doesn't even work out very well when people are talking directly with each other. People and computers, in the ARPA community at Xerox PARC, we came up with the idea of actually taking a visual rendering of what is in the computer's thought cloud and putting it directly on the screen. So this is making a metaphor literal and literally allowing people to point to what they're interested in, allowing the computer to indicate. And this was such a powerful idea, in particular, that once you go to a visual interface, you can deal with things a lot more powerful and dynamic than words or sentences. And that leads to the idea that you might want to, in the future, always mediate communication of all kinds with a computer helping. So mediating communication between two people with the computer helping. Think about what you might be able to discuss about a dynamic, tricky structure like a truss bridge. It would be almost impossible in normal words and language. And these ideas were in a paper that, if you're interested, you can find this on the internet, called The Computer as a Communications Device by Licklider and Bob Taylor. Bob Taylor was one of the funders who followed Licklider at ARPA and also was the person who set up the computer research at Xerox PARC. So this goes back to 1968, and we want to mediate communications between computers and people with computing. We want to mediate communications with aliens and people using computers. And this is something that has actually been left out almost entirely in science fiction literature. And looking at communication between computers and computers, and then we have to establish common ground. And we did this for the internet by coming up with a little Cambrian DNA. If you remember, the Cambrian explosion happened about 550 million years ago, and it was when biology primarily went from single-celled animals to multi-celled body plants. And there was an enormous explosion of species of many, many different kinds. And so to make an internet, you have to have a body plan because we're essentially using computers as cells and tying them together to make a kind of a larger entity. And TCP/IP, which is usually about 20,000 lines of C code, but can be a couple hundred lines of code in a better language, is all you need to put on every machine. And this will allow you to make an internet that has 10 or 11 billion nodes to date and not require any central control to keep it stable. So this was very much a what you might call a biologically inspired computing, not done like most computing is done inside these machines. But the problem of getting computations to act this way, where you have much stronger goals than just sending bit packets around, is still a bit of an unsolved problem, although parts of it have been solved, and it's relevant to this idea of communicating with aliens. So let's take a simple case here of different computers by different manufacturers with different operating systems, or at least 3 different operating systems. There are many apps that create images of various kinds, word processors and desktop publishing, Photoshop and so forth. All of these eventually want to be able to print on a printer. And on the right-hand side, we have many different printers. These printers also have different processors that sometimes will have a standard operating system, but often not. And they all connect to a network, so they're going to have the TCP/IP personality code there. But I think we can see that there are so many degrees of freedom in what you might want to put on a page that trying to have a printer understand a description of every single one of these and to have that description be continuously updated on all printers in the world, it's just not a great idea. So sending a letter, sending a telegram is actually a dumb way to do this. And we realized this the hard way when we were doing this the first time around at Xerox PARC, that we didn't want to send a structure to a printer. So what we really wanted to do was to think about what we do when we have to communicate complicated things long range with people. Is we don't send telegrams, we send an ambassador. We send a person who can negotiate meaning and can carry the larger meaning. And an ambassador is a process. The process can be represented by code that has to be executed at the other end. It can be sent as bits, but it manifests as code. And again, there are too many aliens on the other end. We don't want to have to make a deep interpreter or compiler for every single one of these things. So what we want to do instead is we want to make another little piece of compatibility code here. And that little compatibility code can run a virtual processing unit that's made out of software. And the whole thing together makes a virtual machine. That virtual machine can handle the processes that are being sent to it. And we can do that for all of these machines. Install virtual machines, and the bulk of the virtual machine can just be sent as software. And then we produce compatible kinds of processes that are programs, and all of a sudden we're able to print. And the reason this works so much better than trying to send data structures like XML is that you can make a universal programming language in a very, very small description. And because it's universal, you don't have to change it very much. And so you get this thing where you have a nice balance between what has to be known on the left-hand side, which is something that has to be done in resolution-independent terms, because the screens are all different resolutions, the printers are all different resolutions. You basically, on the left-hand side, do not want to have to know what printer you're going to print on. So that is handled when the process gets to the printer, and it can find out what the printer is, and then it can do the dynamic math to do the scaling and so forth. Okay, so that's an example of, by the way, that thing that it said, the ambassador, is called PostScript, and PostScript was another one of the things that we did at Xerox PARC. So if we go back to typical classical Freudenthal Linkos language of 1960s. Well, he's excused because computers were just getting going in 1960, but Linkos is a very interesting effort in bootstrapping up from a few simple patterns, starting with things that he thinks all creatures who can do anything will find out about numbers. There's a follow-on a few years ago by Longren that takes into account many of the things that happened since Linkos, but in fact it still is basically sending logic diagrams. Instead of thinking about, hey, we should just send a computer, that's the number one thing we should bootstrap at the other end. So we don't want to do that. And just to give you an example, let's take a couple of these situations where we want to send a process into an alien territory. One of them is getting a process from the deep past to work today. So if we go back into the 70s, there were three famous computers that we did at Park. One was the Alto, which was 1973. It was the thing that eventually became Macintosh. We did the first portable computer we know of that would run the same code called the Note Taker, and then a powerful computer towards the end of the 70s called the Dorado. And interestingly enough, software that Steve Jobs saw when he visited in 1979 got thrown away by Xerox. They threw away the disk packs. And one of the disk packs was retrieved, and on it a file was found that was pretty much the small talk that Steve Jobs had seen about 40 years ago. And this file is organized in an interesting way. The system itself is like, this is real object-oriented programming, so there's like an internet of interconnecting and intercommunicating virtual computers. And every part of the Smalltalk system was on this file, including what we would call the operating system and the utilities and the development system, and everything was on this single file. And to run it on these three machines and some of the other machines, it had a virtual processing unit, like I just mentioned. And for instance, to run it on the Note Taker, there would be a little personality code, the Note Taker, that would run the VPU, and the VPU would run all the rest of Smalltalk. And there's one of these for the Alto and one of these for the Dorado. And so when you want to run a system, it would come to you off a file server and would find out what machine it was on. It would look the right personality code, and you'd be off and running, doing bit identical, not like approximations today. And so if we want to run the system today, what we had to do was to get that file and put it on a modern laptop and write a new piece of personality, because these old machines aren't around anymore, get that to run the VPU, and that would manifest this system from the past. And in fact, I have just such a thing here, and let me see if I can get it to come up here. So here it is, and this system is actually running. Here's what Steve Jobs saw. Here's the overlapping windows, the text editing, Smalltalk programming, browser. This system had a character recognizer like that, etc., etc. So this entire system is running as it did back then with the actual same bits. Okay, now get back here. Okay, so you get the idea. So that's how you send a process from the past to now. Now let's take a look at what about sending Smalltalk or some other process into the future. And here we have to take into account that nobody may know how any of this stuff works. And so the question is, how small a piece of personality code could you describe? So here's a one-page, it's probably too blurry for you to see it, but this is a one-page document that describes a very simple computer, so simple that anybody today, we tried it out on students, anybody today can make it run in an afternoon using C or Java or any other programming language around. And that afternoon's work will make one of these guys, it will make one of these guys, that again will run the entire system and bring it to life. So this is, if you think about it, we're in a process now where a lot of the media of the past is actually unrunnable because it's been detached from its operating system, from the computers that used to run it, programming languages and stuff. But here's how we can send archives into the future. Okay, so we want to have some little description here. So this this process hedges the question. It assumes that maybe C won't be around 1,000 years ago, but something like English will be. Maybe not. Who knows what will happen? So we should really think about deeper ways. And again, we might want to go back and think about Freudenthal ways, or maybe Mark Minsky ways. But here's a truly great book. It's worthwhile getting just because it is a great book. It's one of the most fun books if you have any feeling for math. It's a wonderful book in that it does not require you to know any particular math because it is so well written. But it requires a bit of a mathematical turn of mind. And it's about a subject that has not really been talked about much in computing since the 60s. But it's all about how can we make various kinds of universal computing machines. Here is a relatively small Turing machine. It's possible to make one a lot smaller than this. Claude Shannon showed that you can make one that just has 2 states. But more interestingly, Minsky talks about some of the minimal computers you can make. For instance, here's one that only has 3 instructions. Add 1 to some memory word or register, subtract 1 from some memory word register, and take a jump if the register is 0 to some new program location called Q. And you can see, I think, that this could be made into 2 instructions because the last 2 could be subtract 1 from a register and branch to Q if the result is 0. So you can make something very, very small on the operational side, and there are many, many schemes for representing computer memory. This is a griddleization scheme. So if you make the computer memory be all the prime numbers, then the value of each register is the exponent. So the one that's 2 there, that would be location number 0 in the computer, and n would be the value. 3 is the next location in the computer, and the exponent m is the value in that word, and so forth. So there are many different ways of getting a computer directly out of arithmetic without having to go to gates and describe something really complicated. And I think something like that is required because I think what we want to do to send something to aliens is to send them something like that Smalltalk file and make the front of it be the simplest, quickest bootstrap to something that will run the VPU that's there, which will run the whole rest of the system. And that system should be what's now called an artificial general intelligence that can negotiate with the aliens. So we looked at the top 3 books there. I just recommend, there's a paper by Bush and Reddick that you probably know about, which is about testing various kinds of encoding scheme on unsuspecting humans to see if they can recognize that there are numbers, that there are equal signs, maybe the ratio of masses of electrons to protons, and other kinds of pure number constants that might be there. SciTorp, you can look at it online. This is the most comprehensive real artificial intelligence on the planet, the one that has the most sense of the world that humans live in and can reason about that world the way we do. And then Paul Fitzpatrick, when he was at MIT, did a start at thinking about sending programs to aliens rather than just sentences of logic. In all cases, you want to, goal is to get the aliens to build one of those things to build. And by the way, we should expect, if we get signals from aliens, that they will have figured this out. Maybe not, but for the same reason that the scheme worked well with printers, this way gets you a lot further, a lot faster. And what if we have an encounter with aliens? A recent one was chronicled in Arrival. It's from a story by Ted Chiang. And the problem with this is it just assumes the aliens are really a lot like us. I mean, they had tentacles, but they made noises, they made marks of things. And Hollywood is always, and I think fiction writers have had a hard time with aliens because they want the readers to be able to have something in the shared context. So they tend to make the aliens rather humanoid in various ways, maybe with 4 eyes or something. But, gee, the alien could be a flame thing. Could be made out of radiation, and it could think flame-like thoughts, both of which going much, much too fast for our nervous system. And so it's just impossible that to be able to generally handle what aliens might be about, that we could do it with our own very, very slow nervous systems. And we're not that great at learning either. So I think all such communications where we encounter aliens on a starship are also going to be mediated by computers, and with humans, and with machines, and sending things into the future. All of these things are going to require computer mediation. So we come back to Vanguard. First thing after this, we realize, and also after having seen some other science fiction since 1941, Vanguard is self-sustaining. So it has something about thousands of small goals that have to be paid attention, have to be sensed, have to be fixed in order to work for hundreds and hundreds of years. But in fact, it manifests no intelligence of its own. Vanguard, the ship, has no idea that there was a mutiny and there are a bunch of semi-Neolithic savages living on board it. In 2001, there was an AI on the ship, and Hal did have a goal to help humans complete the mission, but Hal had been told that the mission was all important, and so Hal was able to figure out that the mission might go better if we killed all the humans on board. She tried to. And, of course, this goes against a guy who was also writing science fiction about robots all the way back when Heinlein wrote Universe, Isaac Asimov. And so he was ignored for 2001. And then another story that was written back in 1940 by Harold Bates led to the movie The Day the Earth Stood Still, and here we have an AI robot, and we find out that the robot's goal is to protect human civilizations from humans, but the key word here is civilizations. It is quite capable and does kill humans in order to protect the civilizations. It's basically a super cop in the movie. But if you read the original story, it's a little deeper and darker than that. The very last line of Harry Bates's story called Farewell to the Master is this line: "You misunderstood. Mighty Robot said, I am the master." So what had happened was that the humans were actually not in control. They were actually part of the scheme of this much larger civilization that the robots had done. So the last idea here, just to finish off this talk, is to take a look at three ideas here. What's more important? Suppose you had the IQ of Leonardo, but we're born in 10,000 BC. How far are you going to get, especially before you get burnt at the stake or the equivalent? So there are smart people all the way back through 200,000 years, and they had nothing to work with. Leonardo could not design a single engine for any of his vehicles, whereas Henry Ford, who was not nearly as smart as Leonardo, was easily able to build engines and build a lot of cars. Henry Ford was just born into the right century, and that century had the knowledge. And the knowledge came because there'd been a change in context of outlook because of Newton and the advent of science and modern engineering informed by science. So the big deal here is that a change in the context changes radically, qualitatively, the kinds of things we can even think of. So we can think of knowledge as silver, context as gold, and IQ is pretty much lead. I mean, the big bug with IQ is people who realize they're smart when they're young often wind up not learning enough to be able to use their abilities in a powerful way. And this happens in all kinds of dynamic organizations. So here's life on the planet starting a little over 3.5 billion years ago, and going from nothing to something. Still, the organization of that life stayed more or less constant for a very, very long time until multiple body plans suddenly got invented, probably gradually along the way, but not in a way to have critical mass. But once the Cambrian happened, there was an explosion of complexity. Nervous systems got invented for real in the Cambrian, and there have been explosions since. If we go back to our diagram that we started off with, for me, as I became a scientist, I found science fiction lacking more and more for a variety of reasons. If we look at the curve of knowledge and outlook over the last 200,000 years, it again has this incredible takeoff once a couple of critical masses happened. The Greeks didn't quite make it happen, but we needed the Greeks to do the Renaissance And then finally we got past the threshold, and all of a sudden we could look at human beings as being creatures that were primarily mutational in progression to culture. Culture was there all along, but it took off probably when enough of workable language within cultures got embedded maybe 60, 80,000 years ago. Self-conscious invention didn't happen until recently. And now we have self-conscious modification and improvement of the things that chance used to do to our genome. And this is something to think about in our story here. Going back to Vanguard, we have to compare Vanguard with just vision of an improved society inspired by this book by E. Van Vogt, again back in the 40s. But part of the idea that Roddenberry had in Star Trek was that we should be able to fix enough of our behavior to be able to pull out of crises. This was more interesting in the Van Vogt stories because they had some serious crises that had to be dealt with. They weren't dealt with successfully. But today, not that long after Heinlein wrote that story, we now have CRISPR, and CRISPR is allowing us to consciously, by design, to modify our genetic material, even in the face of not understanding how most of our genetic material actually works. We only understand the gene-making part, which is a tiny part of the actual DNA that's actually there. And so, if we go full circle here, we will wind up being the aliens because we will fix ourselves, and maybe badly. But I think by the time that we could fire off a Vanguard to Proxima Centauri in 100 years, we will have wound up doing some serious behavior modification. And how will we then communicate? What will we be as a species when we take hold of our own evolution? Thank you very much. And here's my email address if you'd like to send an email.
Check. All right. Thank you, Alan. That was amazing. That was definitely one of the high points of this amazing conference. Are you willing to take some questions?
Sure. I of course went over.
Pardon? Yeah. Well, we're going to adjust. We're going to make adjustments. I appreciate it. So, are there questions?
This is a question that may be just due to the semantics used, but if you are sending essentially an executable file to somebody else that they're going to run and then is going to upload your ambassador AI, how do you protect from malware and it getting out of the virtual machine that it builds?
Yeah, so basically this is done with PostScript. The whole point of PostScript was to put it in a confined address space. Intel did not do a good job on the CPUs, but the things that are called processes or tasks on your personal computer are in confined address spaces. And so the theory of sending a PostScript program to the printer was to allow it to execute blindly, but completely safe. And then the printer would just print out whatever was in the graphics buffer. The idea was that the program could not touch anything in the printer, but but it could execute to the full extent of its ability in a way that was linear compared to what the print was. And yes, and things would be, we would not have crashes today if Intel and Motorola had done a good job about providing enough address bases. There, in fact, was a computer in the early 60s done by Burroughs, which was uncrashable. Wouldn't that be nice to have today?
Hi, Alan. Thanks for the presentation. I wanted to ask about Licklider's ARPA Dream and how far away you think we are from this, or have we crossed that point already with the internet? Thank you.
Could you just hold it? How far away is the...
Aaron, I don't think he heard you.
How far away?
He was talking to the webcam.
My apologies, sorry. I just wanted to ask about Licklider's ARPA Dream and whether how far away we are from this reality, or have we crossed the threshold already?
No. Well, a couple of things happened on the way to Nirvana. One was the Vietnam War. This turned ARPA into DARPA and killed that funding. Xerox PARC would not have happened if ARPA funding continued. It's tough to do research and but that was a last-ditch effort to at least finish off the first round of 8 or 9 inventions that needed to be done. If you want to see how much is moving, you can go online and type Engelbart, Engelbart into Google and look at the demo he did in 1968, which is 50 years ago next year. And you'll see a bunch of things that haven't been done yet. And the reason is what happened is the stuff at Xerox PARC was so successful and there was so little further research being done that those ideas got commercialized more or less into the pop culture. And the next round of stuff for really augmenting human intelligence didn't happen. Instead, we got something that's rather like the world's most pernicious set of reflecting mirrors for narcissistic personality. That's where we are now. Most people are trapped in all of mirrors, but in science and engineering, the ideas from the 60s that Lick and Taylor and other people were thinking about have happened. For instance, the biology I talked about has happened because of what computers mean to biology, and most science today requires the kind of augmentation that we were talking about back then. But the intent was to deal with the general public because we live in a democracy. And a democracy requires a general level of understanding above a certain threshold or to be successful. That did not happen. And I consider the last bunch of years to be the results of not doing with our educational system what that's been needed.
Another question? Okay, Alan, I think that one more. Philip, come on over here.
Thank you for your presentation, and I had a quick question on what your thoughts were with regards to moral code building within artificial intelligence in the future.
Yeah.
Thank you.
Yeah, well, of course, the biggest problem is AI in a way, is the least of our worries, because consistently shown that people will follow low-wise. And so you don't really need a real AI for it to be dangerous. You just need something that people are willing to follow because it seems to or is like an oracle, or is like a minister, or is like a god. So these are old themes to science fiction people, but we're living them right now. We're right in the middle of it. The thing that was interesting to me about universe, and particularly 2001, because I was a good friend of Martin. He was an advisor to 2009. Some of his ideas were there, but boy, they sure didn't put the 3 laws of robotics in there. It's not that the 3 laws of robotics are perfect. The whole set of Asimov stories were about loopholes that were not anticipated, where the robots wound up doing something dangerous or something iffy because something hadn't anticipated. And all of these, Asimov was a biochemist, and so he had very high appreciation of how tricky systems that have lots of feedback can be. And so they were partly about careful what you think you're doing when you set down principles that you have open-ended mechanisms following. We were very careful when we did the internet. So consider the internet as a computing system that has to balance the message traffic without having any central controller, without having any way of knowing what's going on at any instant with about 10 billion nodes. Think about that. That balancing and retransmission and delays are done by each individual node solely from information that they're able to gather from what's going on around them. And that was not easy to do. It took a couple of passes. The first version of TCP did not have all of the heuristics needed. Still, it's about 9 heuristics to do the whole thing. And it's that other big idea about systems. Zeroth idea about systems is most dynamic systems, places where they're coupled. The other interesting thing about systems is it's possible to organize complex systems to damp out the errors rather than to propagate them. This is the whole idea of error correcting codes, and the fact that the internet works, and the fact that it worked for many decades, could work forever. So all of these ideas are cautionary tales. I think the simplest thing to say about computer people is they don't think about this at all. Most computer people just do little hacks onto the system, and I dare say most computer people don't really understand how the internet works. I say that because almost no other computer code that I know of is written like the internet, despite the fact that the internet is the most scalable computer artifact ever done by magnitude. I think we have levels of culture here. And my experience with graduate students, they don't think the internet is a computer artifact simply because it doesn't break. It's the only computer thing they've ever seen that doesn't break. So they think of it as something supplied by the gods. About 35, 40 gods are dying off, so it's going to be a quick myth in another 10 or 15 years. Skynet, here we come.
All right. Any other questions? Alan, I very much appreciate your time on behalf of Icarus Interstellar and Starship Congress. Thank you very much. Alan Kay. signing off.